to another the rate of reaction based on volume of gas collected. So remember last week I gave you an example where I actually explained to you measure the rate of reaction. One specific example was the release of gas, right, when zinc reacts with hydrochloric acid. Yeah. Yep. Rates of reaction. Chapter 7. Yeah. Then here you go. So Zn plus 2HCl, you get ZnCl2 plus H2. Okay, last week I show you. I only got 5 extra copies. What was the I gave you guys last week? One more stack I gave you all last time. That's chapter 8, yeah, that's chapter 8. But chapter 7 already. Here got extra. You only did last week, right? I give you, I go bit for you. Those who have things. I got one left here. Anyone don't have? All right. Okay, so the second way of calculating the rate of reaction is to collect volume of gas. So I'm going to separate this page. This is last week. So to calculate rate of reaction, another way is you can have, for example, a test tube, and then you have a delivery tube into a gas syringe. Although your book might give you a different outcome where they will actually use a burette instead, but I'm going to use a gas syringe, it's easier, okay? So imagine now you have your acid inside here. Okay, you have your acid inside here, and then you have zinc granules at the bottom. So there'll be bubbles of gas release. So then the gas release will be transferred into a gas syringe. Okay, so the gas syringe will have a scale there as well for you. Okay, so this will be your HCl. And this will be your zinc. Zinc pieces or whatsoever. And this is a gas syringe. Gas syringe is not a very popular example in SPM, but it's normally used for IGCSE. So just remember that you have another method of doing this, which is to put into the burette, okay? Right, so how is this done? Very simply. So you can just start, you can just say that I'm gonna put this on top with so you say rate of reaction can be calculated or can be measured also, can measured by collecting gas in the gas syringe as the hydrogen gas is released during the chemical reaction. Sorry? Right side, the release of gases, the volume of gas release. Usually, mass loss is an alternative only. Commonly, yes, commonly the right side. But like I said, it's possible to ask from both. But usually on the left side one, the one I showed last week, which is the mass loss over time, that's usually used as an alternative answer. Yeah, meaning, for example, they ask you to suggest another method of measuring rate of reaction, that could be it. Yeah, if they ask you, like, for example, this is what they give you in exam, but they ask you for an alternative method to measure rate of reaction. No, this is the real one. This is the commonly asked, commonly shown. The other one is the one that they will usually ask you to write as an alternative method. Okay, all cool, Kenna? So now we're going to move on to the next one. Okay, so let's take a look at the rate of reaction graphs. Now, to measure the rate of reactions, we can either calculate the reduction of reactants over time or the increase in product over time. So there are two different graphs that you can see over here. Now, usually the graph is drawn as something like this. Let me show you up. Quantity of reactants, yes. Quantity of product is supposedly directly proportional to a certain stage. But no, my point here is I'm going to show you a graph. So you can actually calculate concentration of reactant or volume or mass, it doesn't matter, any one of these factors. And this is time. So I'll use two different colors here. So for example, the amount of reactants that you have will drop over time, and the amount of products will increase over time. But you can see, right, they're actually proportional to each other. I mean, they're not proportional, sorry, they are actually, one will increase and one will decrease, okay, according to the same level. So as the reactants are used up, the amount of products will actually increase over time. Okay, that's how we see it. So based on this, we can separate it out into different. This one. We can separate it out into two different graphs over here. So what you can see over here is that the quantity of reactants will definitely reduce over time, right? Because more and more reactants are being used up. While the quantity of products will increase over time in this manner. But you will notice, right, the quantity of products don't increase forever. Up to a certain point, you will notice that it becomes flat. Okay? So why does it become flat over time? It's because correct. So you'll notice that there's a flat point, the products being formed, and then the rate becomes 0. So whenever the rate is at that point, at a flat point, we say that rate is equivalent to 0. Same goes for here. When it becomes flat, eventually we will say that rate is equivalent to 0. Okay. So once there's a point where it comes flat, which means the maximum volume of gas is collected. Now, there's one more thing that I want to explain to you, okay, that you need to know, is that if you were to calculate the rate of reaction later, right, I'll show you what. Your graph will look something like this. It will go off flat until this point here, right? But once it reaches, right, most of the time, we say, okay, because this is timer, right? So the question is when does the rate of reaction complete? When is the reaction complete? You will notice that they will show you up to like extended point of time. During this time, there's no more rate already, correct? So we said that the rate has already reached, the reaction is complete when it starts to approach rate equivalence to 0. So supposedly at this point over here, which I'm going to label it as T1, T1 will be the time where the reaction is complete. So when you calculate, later I'll show you, when you calculate overall rate of reaction, you will not take the time up to this end over here, which is T2. We're not going to take T2, we're going to take T1 only as our time taken for the whole reaction to complete. So that when you calculate the average rate of reaction, you're going to take the total volume of gas collected, for example, over the total time for the reaction to complete. And in this case, it will be T1 and not T2. You understand? That's something that you must remember in case they ask you this question in the exam. Most students will forget. Okay, meaning to say, right, when we calculate rate of reaction, we want to make sure that there's a total time taken for the whole reaction to complete. Do you understand what I mean? For example, if I put zinc inside into hydrochloric acid, there'll come to a point where there's no bubbles being formed anymore. That's when I know the reaction is complete. But the question is, the graph will not show you up to only that point. The graph will show you even after that, not extended beyond time. But the extended time doesn't calculate, you cannot calculate that into your rate of reaction because the reaction is already complete. So what we do is that we'll take T1 as the part where it's complete into our calculation. Later I'll show the formula. Okay, now, how do we interpret graphs? Sometimes in your exam, they will also ask you to predict another reaction, similar reaction, but maybe faster or slower reaction. So they will ask you to sketch another line on top of the existing line. So you need to know how to draw the lines also. Based on the first graph on the left, you will notice that there is a blue line and there is a red color line, which shows you the rate of reaction also. Okay, you can see in this case now, it is the reduction of the quantity of reactants over time, correct? But you can see that there is a red line and there's a blue line. So the question now is to know if the rate is fast or slow. All right, to know if the rate is actually faster or slower, you will need to see how steep the slope is. So I'm going to give you a hint over here. I'm going to give you an explanation over here. Steeper slope equals to higher rate of reaction. Okay, steeper slope is equivalent to higher rate of reaction. Or we can say that higher gradient equals to higher rate of reaction. So if it's the opposite, which means the less steeper it is, the lower the rate of reaction, or the lower the gradient, the lower the rate of reaction. So look at the blue line. Let's take a look at the first one, the left side first. Okay, look at the left side. We have red and blue line, right? Which one has a steeper gradient? Or which one has a steeper slope? The blue one has a steeper slope, okay? So the blue one has a steeper slope means the rate of reaction is higher. And also, if you notice, right, if you don't understand what I just said, you can look at it in the simple terms, okay, in terms of simple terms. You can see that the blue line the reactants actually decrease much faster compared to the red one. You understand? Right? So the blue line shows you that the reactants are decreasing much faster compared to the red one. If the reactants are decreasing much faster, meaning the rate of reaction is higher. They use up, the reaction uses up the reactant much more quickly compared to the red one. You understand what I mean? So that tells you that the blue line shows a higher rate compared to the red one. On the other hand, we can also calculate rate based on the quantity of products over time, right? So you can see over here, they both reach the same point eventually, which is this point over here, right? But the question is, which one reaches faster? So you see in this case, right, same thing also, the blue line has a greater gradient, or it has a steeper curve. So that tells you that the blue one is much faster compared to the red one. So we said that the steeper the gradient, or the steeper the slope of the line, the curve, then it has a higher rate of reaction. Very simple also. Okay, either decrease in quantity of reactants or the increase in the quantity of products. That's it. Clear? Questions? If you have any, before I move on to the calculation part. Okay, yeah, so take your calculator. So the next part is called calculating rates of reaction. No calculator. Hey, I tell you, rates must calculate stuff, ma. Yeah, go phone, ma. Use phone. You just have to divide any, yeah. It's very simple. Just divide any, yeah. Okay. So rate of reaction is the change in quantity of reactants or product over time taken. Okay, the change in quantity of products or reactants over time. So which means you're going to see either you want to calculate the reduction in the reactants over time, or you want to calculate the amount of product that is being formed over time, either in a form of loss of mass or in a form of collection of gases, up to you, okay? So the first one we're going to explore is called the overall rate of reaction. Overall rate of reaction is also known as the average rate of reaction. From now on, I'm going to say rate of reaction as ROR, okay? I'm going to cut it short, but do not use short form in exam. Use the long term. Just that I want to cut short the time, so I'm going to write ROR. ROR stands for rate of reaction. In my case, only don't write in exam. ROR cannot be used in exam. So you have 0.3 grams of magnesium ribbon reacts completely with excess dilute chloric acid, hydrochloric acid in 30 seconds. Calculate the rate of reaction. So in this case over here, the overall rate of reaction is equivalent to mass, okay, mass of magnesium over overall time taken. So we saw that the mass of magnesium in total was 0.3 grams. Divide by total time taken, which is 30 seconds. So if you use a calculator, you can see that your rate of reaction is 0.01 grams per second. So this is your answer. Depending on what unit you use, because this is mass, and this is in seconds. So your unit for the rate of reaction is grams per second. But it can be also cm cubed per second and so on. All right, so you remember that. Okay, this is the easy version lah. Okay, the harder version is later on. I'll show you some examples. So if you go on to the next page, you'll be able to see we're going to learn how to calculate average rate of reaction given a certain set of data or a graph like this. So usually in chemistry exam for your rate of reaction part, they will either give you a set of data or they'll give you a graph like that. Sometimes they give you the set of data in the form of a table. They will ask you to plot the graph for yourself. You understand? So which means they will give you things like, example only, volume of H2 and time. Okay, example, volume of H2 and also time. So for example, what happens here is they'll maybe show you, okay, at first is 0 and then 0. And then for example, 10 cm cubed. And then it takes here maybe 5 seconds. And then 20, 10. And then 30, 15 and so on, right? Then you have to transfer this information to a graph form. Okay, either they give you this data or they will ask you to, they will give you the graph straight away. But most likely in exam, most of the time, they will give you a set of data. They will ask you to plot the graph yourself. So you have a graph paper lah. Okay, so now assuming that we skip the data part, we plot the graph already, how can we calculate the average rate of reaction for different cases like this? Okay, so remember, let me just remind you one more time in case you didn't pay attention just now. See this graph over here plotted for you already. When is the reaction complete? When is the reaction complete? And 180 seconds, correct. The point where it begins to turn flat, that is the end of the reaction. Once the graph turns flat, rate of reaction is 0. The reaction is complete, the rate will be 0 already. So the total time taken for this reaction is actually 180 seconds. And the maximum volume of gas, how much? 35 cm cubed. Very good. All right. Now, let's learn the calculate stuff. There are a few keywords that you must memorize. If you fail to do so, you will get wrong for your calculation. Notice that there is for the, there is in the. Two separate terms. Again, you have for the, and you also have in the. They have different meanings. And I'm going to show you what happens. Okay. When they say for the first minute, for the first 2 minutes, this is total time up to that point, correct? Okay, total time up to the mentioned time, which means up to the first minute, up to the second minute, up to the second minute. Okay, total time up to the mentioned time. If you see in the, correct, it is on that 1 minute itself. It can be second or so, but second one is usually I'll explain to you more. Okay, for the specific minute. So before we start, I'll explain to you one by one. For the first minute means, for example, the first second up to the 60th second. That's the time frame for A. Okay, and then for B, it will be the first second up to the 120th second. You understand? And then for the in the part is, for the second minute means it is actually 61 to 120. You understand? For the third minute, it will be 1 to 1, 280. So this is for A, this is for B, this is for C, and this is for D. Okay? For E, the whole reaction is the same thing as what we talked about just now, which is the first until the 180th second in total, and also total volume. That is for E. E is the easiest actually. Okay? So let's do one by one. So A, for the first minute, it will be 60 seconds. So mark at that point where you get 60 seconds. So at the 60th second, I'm going to use a different color because it's going to be red line, so it's going to be hard for you to see. All right, for the 60 seconds, it will be here at 0.20 cm3. So for A over here, rate of reaction is equivalent to 20 cm3 of gas release divided by 60 seconds. So you have 0.33 cm3 per second. So that's your first answer. Cannot, must follow the graph. If the graph uses second, you use second. If the graph uses minute, you use minute. Unless they request specific one, correct. Okay, I'm not saying that minute is wrong. I'm saying that follow the graph of all the unit they give you. If they give you in cm3, then in seconds means you must calculate seconds. If they give you a minute, then you calculate minute. So for the first 2 minutes will be 120 and 30 cm3. So for B, rate of reaction is equivalent to 30 cm3 divided by 120 seconds. So that gives you 0.25 cm3 per second. Okay. Okay. And then for C, in the second minute, so in the second minute, we have to take 2 points, 60 and 120, 20 and 30. So we're calculating the rate between this point over here. You understand? Between these 2 points. So right now for C, you pick the 2 points. Average rate of reaction will be 30 minus 20. Yes. Divide by 120 minus 60. Sorry. So that would be 10 divided by 60. Your answer should be 0.167 cm3 per second. It can also be 0.17, up to you. Okay. Okay. And then for donkey, in the third minute, you have to take what? You have to take the second and the third minute, which is 30 and 35. And then you do the same thing also. Okay. So rate of reaction will be 35 minus 30 divided by 180 minus 120. So it's 5 divided by 60. You get 0.083. 0.083 cm cube per second. So that is your answer for donkey. Okay, the last one is the easiest, like I said just now. Find out when does the reaction complete, and you say that it is actually 180 seconds, and the total volume of gas collected is 35. So all you have to do is to calculate the total time taken and total volume of gas. So that will be 35 cm cube of gas divided by 180 seconds. The answer is 0.194 cm cube per second. So that's how we calculate the average rate of reaction in each and every different case. Yeah, sure. All right, questions? No, okay, all right. Then we go to a harder one. So we have done what just now, all of these examples here that I show you, they are all called average rate of reaction because they take an average value for a certain time frame. Okay, again, it's called average rate of reaction because we're taking a certain time frame or to calculate the rate of reaction. The next one is called instantaneous rate of reaction, where we're going to calculate rate at a specific time. Like, for example, what if I want to know what out of the 180 seconds is now, on the 167th second, what is the rate of reaction? We can actually do that, all right? But first, we need to have a graph. So in this case here, once you get a graph ready, this is an example, okay? Imagine that you have a zinc reacting with dilute hydrochloric acid. Same thing, you have Zn plus 2 HCl. You're going to get ZnCl2 plus H2, right? So the volume of gas collected over time is what we're going to use to calculate the rate of instantaneous reaction. Instantaneous rate of reaction. Okay, so this is okay. Now, why do I show you this picture? You notice that this picture is different than the one I draw earlier. The one that I draw earlier was a gas strange. So like I said just now, right, the gas strange version is more common in IGCSE. So for my IGCSE students, I give them the gas strange version. For you guys, right, the SPM one, for SPM, this is more common. Yeah, the burette version. So in SPM, they would like to use this burette setup, which is much more complicated, in my opinion. Okay, but that doesn't mean it's wrong. They are both usable. How does it go exactly? Nothing. It's the same thing. You have a delivery tube that delivers the hydrogen gas into the burette part, but the burette is immersed inside water. So as the gas is collected above inside here, you can actually measure the volume of gas also. It's just that the gas strange is a much simpler setup. So you don't have to actually set up a water bath. You don't actually need the what's it called? The burette inverted and stuff like that. So less tedious stuff because less things are being used. Okay, now, assuming that we already did the experiment, assuming that we have a set of data already, then assuming we've already plotted the graph, how are we going to calculate the instantaneous rate of reaction? So this graph shows you the volume of hydrogen gas collected over time based on the reaction just now, okay? And also based on a 40-second interval of gas collection. Then you plot this graph already, assuming that you did lah. Okay, now we're going to use this graph to actually calculate the instantaneous rate of reaction. I'm going to do A for you guys to see, then you'll try B. And then I'll explain to you that your answer can be different from your friends. Yes, there is no one specific answer. Of course, in the marking scheme, there'll be an answer there, but a range of answer is acceptable. It is actually based on how you plot the graph actually, and also how you draw the line. To calculate instantaneous rate of reaction is usually what they'll do is that in exam, they'll give you a very specific time that they want. For example, you see here, they wanted to calculate the rate of reaction at the 60th second. So you see this graph over here. This is 20, this is 60, this is 100, and so on, correct? So I'm going to focus on 60 right now because that's what they want. So at the 60th second, the graph is over here. Do you see that? This is the graph. What I'm going to do is I'm going to draw a straight line across that point, but it must be overlapping with the curve. So what I'm going to do now, I'm going to draw a straight line across. I'm going to adjust the line, don't worry. Okay, do you see that? So you notice that my line is touching the point that I actually cross, which is at the 60th second. Do you see that? And then once I draw the straight line across, it will look something like this. Now, to calculate instantaneous rate of reaction, you have to calculate the gradient of the straight line. Use a ruler. Okay, now use a ruler, draw a straight. Hey, use pencil, don't use pen. Because there is two questions here. 60th second and the 120th second. So use a pencil first because later you'll rub off the line and then do another one. Okay, you see this X over here? Okay, now I'll show you. Imagine this is your curve. Okay, imagine this is a curve. If the point that you want to plot is here, I mean, the point that they ask you is here. Right, you see, right? 60th second, ma. So this is 60th second, ma. So if you found a point at the graph already, your straight line should be, your ruler supposed to go flat on this part over here. Sorry. Your line is supposed to go flat like this. Okay, understand? Meaning, take a ruler. Okay, make sure a ruler touches the middle part over here, which means imagine right now your ruler is this like that, right? Here's a ruler, for example. You align your ruler in the middle, touching this point. Okay, this is a ruler. Take a ruler, align the ruler where the middle part of the ruler is touching against your X. That's touching against the curve. Then you draw one straight line across. Okay? Now, to know if your line, your straight line is good or not, to get a correct answer, for example, my hint, my tip for you is that you're going to make sure that your angle on both sides is about the same. All right? The angle between the straight line that you draw and the curve should be about the same for both sides. Okay? So if you're safe, for example, if you're not satisfied and you realize that maybe the line is tilted towards the top or to the bottom, you can always redraw the line. That's why I say use pencil. For example, now, right, you say, okay, I'm not satisfied with my line. I would like to draw a new one. So I can take my ruler, I can draw another one across. Okay? So if I don't like it, I can always just change the position of the line to my liking. For example, like this. But it's up to you, like I say, it's up to you, okay? Okay, everyone done with the lines? Yes. Okay, yeah. All right. Now that you know, understand already. Now, to calculate the instantaneous rate of reaction for the 60th second, we're going to calculate the gradient of the straight line that we just draw. So I say here, gradient of straight line. Okay, gradient of, don't write an inside line, right outside. Huh? Gradient of straight line equals to instantaneous rate of reaction. Anyone wants to remember how to calculate gradient? So you remember last time we have the formula where we calculate the gradient based on y is equivalent to mx plus c, remember? So we're calculating m over here. To calculate gradient m, it is equivalent to y2 minus y1 over x2 minus x1, where your y1 and y2, your x1 and x2 is the coordinates across 2 points on a straight line. Okay, m is gradient. So right now, for example, how do I get the 2 coordinates of my choice? You can do any values that you want, but it must fall under the straight line that you just draw. Okay, not the curve on the straight line by itself. So for example, I'll pick 2 points, which is easier for me to see the coordinates. So maybe I'll pick one over here. So the first one over here that I have will be, this will be 100, right? So my x value will be 100 and my y value will be 43. Okay, and then I'll try to pick another one, maybe over here. Okay, so at that point here, it will be 20. So my coordinate for the second one is 20 and 23. So now I have my x1, y1, x2, y2. Okay. Now, again, you can choose any point that you want across the line. You want to choose here, can. You want to choose here, can. Up to you, doesn't matter. So I choose the 2 points. You want to choose your own point, no problem, okay? But it must only be points on the straight line. Okay, now that I have my own values, I'm going to calculate my gradient based on the values that I have. So the gradient for this line will be 43 minus 23 divided by 100 minus 20. So that'll be 20 divided by 80. It will be 0.25 cm cubed per second. All right. I'll explain to you afterwards.
Can we pick any 2 points?
Any 2 points across a straight line, correct? Up to you. Okay, try to get different points, see, compare. It doesn't matter, you know why? Because in the end, your gradient is the same. Whether whichever value that you pick, right, you still get the same gradient. So don't worry. Okay, the answer in the marking scheme for this question is 0.25 exactly, which means I got a perfect answer. But again, later I explain to you, it doesn't have to be exactly at 0.25 because you can actually change. You can get another value out. All right, I'm going to go around and see your lines, and I will make comments about your line. Okay, okay. Now, try to align things to make sure that it is medium. Then you align. Then you pick two coordinates. This one, okay, not bad. Wait, don't mind. How many is? Okay. Like the same. Oh, okay. One is like is large. You put the okay, if you use your own coordinate and you get plus minus 0.01, 0.02, acceptable. Okay, say for example, your answer is 0.26 or 0.27 or maybe 0.24 or 0.23, about plus minus 0.1 or 0.01 or 0.02, acceptable. Anything beyond that, like for example, 0.3 cannot, or 0.4 cannot, or 0.1 cannot. You understand what I mean? Now, how are they going to mark this question? Or why cannot take any 2 points on the curve? Okay, because we are calculating time rate of reaction based on that very specific time. So for example, my specific time right now is the 60th second. So at the 60th second, we are calculating, I'll show you. You imagine the curve, imagine this is your curve, right? And then you put an X over here. We are actually calculating the gradient for this single dot over here. But you see, right, the curve itself is not a straight line. We cannot get the gradient of other points of the graph. We just want the gradient for this part over here. But you can't calculate gradient based on one single point on the curve. So that's why what we do is that we actually draw a straight line across so that we know what is the gradient for, maybe, for example, this part to this part over here, very small section of it only. But you can't do that if you were to use the curve. We have to use the straight line to calculate gradient. Even if you remember, if you were to do math, remember, calculating gradient means it's actually of a straight line. So in this case, also you must use a straight line to calculate the instantaneous rate of reaction. So you must, no choice but to draw the straight line. You will get a wrong answer, supposedly. All right, not supposed to do that. You understand? If you draw the curve one, if you calculate the curve one, right, you'll get a very larger, much larger value because the difference is too much. Okay, all right. If you understand what is said, then please try the second one. B. I will not draw mine first. I'll let you all do first, and then I'll check for you all. I'll give you about 5 minutes. Yes, yes. So either you rub off your existing line or just continue drawing up to you. I saw some of you draw 2 lines in it. Just draw 2 lines, okay? $240, why? No, yeah, it's 120 any value on the line, correct? But you must draw a straight line first. Yeah, I'm already now. The marking scheme's answer is 0.11. It's okay, it's okay. If it's a bit different, it's okay. What? Plus. Should be okay. Should be okay. So for the 120th second, again, the marking scheme answer is 0.11. So now I'm going to use to see what I get. 125. So mine will be 50 minus 43. And also 180 minus 120. That'll be 7 divided by 60. So mine is 0.7 1, 2. So you see mine also not 0.11, ma. Mine is 0.116. So mine is 0.117 actually, but it's very close, so acceptable. 108. 0.108. So 0.11, right? Round the nearest to the small points. 0.13, okay? 0.02 difference. Huh? Up to you. Any points you take from the graph in the straight line, you still get the same gradient. 0.25, well, that's very far away already. Which means your line is wrong. Your line is wrongly drawn. Anyone else with different answers? Let me share with me. I'll let you know what's correct or wrong. 0.09 is too low. Not acceptable. 0.1375 is round off is 0.14. Slightly too far away. All right, try to adjust your line a bit. Hey, if you guys get different answer like way off 0.11, try to redraw your line, okay? Now, a common tip that I can give you is this. When you draw the line, like I said before, try to make sure that the angle between the curve and a straight line is about the same. If it's too much different, redraw the line. That's the tip I can give you. Now, again, you can see here, my second calculation is not perfect. The answer is 0.11, but I got 0.167. It's 0.1167. So I would say that mine is about 0.117. Okay, so it's 0.12 round off. So it's okay. It's just 0.01 different. So those of you get 0.01 plus minus or 0.02 plus minus, okay, acceptable. Okay, clear? Questions? No, all good, can I? Okay, if you can, then we're going to move on to the next topic already, which is called the factors affecting rate of reaction. Okay, now for the next part, no more calculations. The calculation part stops here. So let me just recap one more time. You have average rate of reaction, where we calculate the rate of reaction on average for a certain time frame. And then we have instantaneous rate of reaction, where we calculate the rate exactly at the dot for a specific time. Like I said just now, for example, on the 60th second, at the 120th second, the key term is at the, all right, at the 120th second, at the 60th second, at the 30th second, and so on. All right. Now let's move on to the next one, which is called the factors affecting rate of reaction. In this particular subtopic, we will be discussing what are factors that can affect the rate of reaction and how we can maybe try to manipulate the factors to increase the rate of reaction. Sometimes the rate can be too slow. We want to speed up the rate of reaction. What can we do? We can actually manipulate the factors over here. So there are several factors that we're gonna discuss. Number one is surface area. Number two is concentration of reactants and gas pressure. The third one is temperature. The fourth one is light. And the last one is presence of a catalyst. Okay. Now, before I go on, I need you all to understand. Every single factor that I'm going to discuss is going to be based on collision theory. Okay, all of the things that I'm going to discuss is based on the collision theory. And also kinetic theory of matter. Okay, collision theory is for all. Kinetic theory is only for temperature. So they're related to these two different theories. Okay, let's discuss the first factor, which is called surface area. Now, for surface area, you need to be very aware of two different terms. There will be surface area, and there will also be size of particles. Size of particles. Now, before y'all forget, I'm going to explain to you straight away. Surface area is not equivalent to size of particles, because a lot of students get confused at the end of the chapter. They think it is the same thing. Okay, surface area is inversely proportional to size. Okay, surface area is inversely proportional to size, which means when surface area increases, the size of particles should drop. The size of particles increases, the surface area will drop. Okay, so please remember this key term. Don't forget until the end. Now, let's take one example, which is the same one as earlier, but we changed the substance a bit. Calcium carbonate reacts with hydrochloric acid to give you calcium chloride, carbon dioxide, and water. Okay, so limestone is also known as calcium carbonate. Now, if you were to dissolve chunks of salt or powdered salt, which one dissolves faster? Powdered salt, correct, right? If you were to use cubes of sugar or granules of sugar, which one dissolves faster? Yeah, granules. Between granules and powder? Powder. Okay, so you understand, right? We have powdered form, we have granules, we have chunks, we have cubes, for example. Okay, so which one has the smallest particle size among all of this? Which one? All right, example, we have chunks versus granules versus powder. Which one is the smaller size? Powder has the smaller size. Now, when you have powder substances to react, for example, calcium carbonate can be found in different sizes, right? You have big chunks, you have smaller granules, you also have powdered form where you can grind completely, okay? So if you were to react any of this with hydrochloric acid, you will see different outcomes. Meaning to say, for example, if you use chunks, you will see lesser bubbles appearing compared to maybe you use powder. There's more bubbles appearing in a shorter period of time. So which one has a higher rate of reaction? The powdered form or the granules? Powdered form. Very good. Okay. So very subjectively, you can also just look at the tubes and tell me which one has a higher rate of reaction. If you go to the next page, you'll be able to see. So we have tube A and tube B. Which one has a higher rate of reaction according to what you see? A. Why? More bubbles can be seen forming in a shorter period of time. So supposedly, if we use powdered versus granules, the one over on the left side will be powdered limestone. Okay, the left side will be powdered limestone. I'm going to use calcium carbonate, okay? And the right side will be granules. Okay, but like I said, we cannot just assume the rate of reaction is higher than the other. We must use we must calculate lah. But in this case, we don't want to calculate anything. I just want you to know that if you use powdered form, it has a higher rate of reaction compared to using granules or chunks. On the right side, I just want to show you that besides looking at the bubbles, we can also measure the mass loss of reactants to check or to measure the rate of reaction. So the faster the mass loss, the faster the rate of reaction. The slower the mass loss, the lower the rate of reaction. You understand? The faster the mass loss, the higher the rate of reaction. The slower the mass loss, the lower the rate of reaction. Mass loss, correct. Because you see this now, right? We said that calcium carbonate reacting with hydrochloric acid will release out gas. The gas will evaporate off into the atmosphere. So based on the law of conservation of mass, there should be lesser mass over time because the carbon dioxide is evaporated off. You understand? So again, to calculate rate of reaction, you can have either calculating the mass of or the volume of carbon dioxide gas release or produced, or you can calculate the loss in mass of the reactants over time. Either one of these, both can be used. Okay, so you all will know lah, based on the graph plot. You see here, right? This is the graph. Powdered limestone will be the one in number one, graph number one, and lumps or granules of limestone will be number two. Okay, as I've already explained to you the shape of the graph, you all should understand that, technically speaking, the powdered one will be the one that has a higher rate of reaction. Why? Because there's a much faster increase in products over time compared to the other ones. Okay, do you understand? But one thing that you must notice is, okay, if you want to calculate the rate of reactions fairly, you have to keep something in constant, which is mass of the calcium carbonate as well as one more thing. Huh? Measuring tool? No. Besides, okay, now what are two reactors that you have? Calcium carbonate and? What is the two reactants? Limestone and what? The two reactants. Look at the equation. What's the two reaction? The acid, correct. So what about acid that you need to keep constant? Volume, number one, some more. Concentration, very good. Yes, molarity, correct. So you have to keep the mass of the limestone constant and the molarity or the concentration of the acid constant, volume as well. Then you will be able to ensure a fair test for both. That's why you see the graph is never higher than the other. I've seen students draw the graph, right? They'll actually they will sketch a graph, one higher than the other, because they assume that there's more products being formed. No, the amount of products remain the same because the amount of reactants that you use is the same. The only thing different is the total surface area or the size of the particles is different. That's it. So if you use equal mass of substances, either powder or lumps, and you use the same concentration and volume of acid, you should get the same amount of products. So if they ask you to sketch a graph in the future, make sure that if this example comes out, you have the same amount of reactants and the same amount of products in the end, which means they will reach the flat point in the same level, but the one that has a higher rate of reaction will achieve it first compared to the other one. So again, notice that there are two graphs actually drawn in this part over here. You will notice that for the powdered limestone, it reaches the flat point faster compared to the other one. So which means for powdered limestone, the end of the reaction is over here. It takes around, say, for example, 2.5 minutes or 3.75 minutes for it to finish up the reaction. Whereas for the lump limestones, it takes around 5 minutes to complete the reaction. Sorry, 5.5 minutes to complete, which is over here. So that means that powdered limestone finished up its reaction faster compared to the lumps of limestone. But you notice that they all reach the same level of products. Understand? Okay, so this is how we interpret the graph itself. Clear? So what are the possible questions they can ask you is to sketch another graph on top of the existing graph. Okay. Okay, cool. Okay, so again, possible questions they can ask you in the exam is they will ask you to sketch a graph. They'll give you one curve already. They will ask you to sketch another one, either lower rate of reaction or higher rate of reaction. So if it's higher rate of reaction, you're supposed to sketch the graph above the existing graph. If it's lower rate of reaction, you're supposed to sketch a lower one. You understand? Okay. Now, knowing how to interpret the graph is not enough. You need to know the mechanism of rate of reaction. So number 9 here is very important. We can say that limestone powder has a higher rate of reaction compared to lumps. But why? Okay, this is when students get confused. Okay, you have to make sure you understand what is particle size and what is the total surface area exposed. Okay, when we say particle size, we talk about the size of the reactants, which means, for example, powdered means very fine particles. Chunks means huge particles. So between chunks and powders or limes and powder, you will have different particle size. But the total surface area exposed for reaction is different for both. Okay, so total surface area exposed, all right, for the powdered one is way larger compared to the chunks or the lumps. Do you understand? So this illustration here will explain to you how this actually works. Imagine you have a chunk of limestone. The acid can only react with the surface area that's in, right? So for example, if you assume that it is a cube shape, you ask yourself, how many surfaces does a cube have? 6 surfaces, correct? So assuming that only 6 surfaces are available for reaction, then that's the only reaction that you get between the acid and limestone. But if you cut it into 3 pieces, all right, you see here, you got 6 surface area, right? 6 surface area. Right now, you got 6 times 3 surface area. How much is that? A total of 18 surface area to react. And if you were to cut it even smaller and smaller and smaller, won't you have a larger surface area to react with? That's how you should explain it in exam. So usually if this question comes out and asking you to explain in terms of mechanism, you will need to explain 2 to 3 marks. The 2 to 3 marks comes from explaining this whole thing with relation to collision theory. So meaning to say, you have to explain first of all why powdered limestone can react better with acid compared to lumps. The answer here is it has more surface area. Okay? When there's an increase in surface area, you must understand that now the particles will collide even more with each other. So the first one to explain surface area, right? Expose, and then explain the second point, which is an increase in the number of collision between the reactant particles. And then lastly, if you increase the number of collision, you will also increase the number of successful or effective collisions. With this, you will score 2 to 3 marks in total. Only if you hit all 3 points, you can get 2 marks. If you write only 1, which is surface area, you get only 1 mark. And then if you come back and tell me why I don't get these 3 marks, it's because you didn't explain about the collision theory, which many students in the past have asked me the same question. How come I write this answer more surface area, but I didn't get full marks? Because you didn't explain about the collision theory. That's why initially I told you about collision theory and kinetic theory of matter. You have to include this into your answer if they mention the word collision theory. Okay? So in the future, if you come back and ask me again, how come I didn't score full marks for this question, I'm going to ignore you. Because I already explained to you many times. You have to relate the collision theory, especially for this chapter. Okay? Clear? So therefore, it will increase the rate of reaction. So let's recap a bit. Smaller particle size, larger surface area to react with, more collision between reactant particles. This increases the number of successful collisions. Done. Particle size reduces, more surface area to react with, increases number of collision between reactant particles, increases the chances of successful collisions. You have to mention all 3 points. Okay? Clear? Any questions? We'll move on. Now, for the next few factors, you realize that the explanation is about the same, which makes your life so much easier. Next, concentration. Concentration can also mean molarity. Yeah? Yeah, our class end at 10:15 today. You know, right?
Yeah.
Class extended to at 10:15.
Oh, yeah.
You want to go tell us? Tell now. I got half an hour left. Tell. Okay. We are moving on to another example. A yellow precipitate is produced in a reaction between sodium thiosulfate and hydrochloric acid according to this chemical equation. Na2S2O3 plus 2HCl, you'll get NaCl plus sulfur plus sulfur dioxide and water. Sodium thiosulfate reacts with hydrochloric acid to give you sodium chloride, sulfur dioxide gas, and also water being produced. Now, we're going to focus on the sulfur being produced. Sulfur is insoluble in water. Okay, sulfur is insoluble in water. So when you add sodium thiosulfate and hydrochloric acid together, there will be a formation of yellow color precipitate. That's why I mentioned here a yellow precipitate is produced. Okay, how do we calculate the rate of reaction for this one? We're going to calculate and see how fast the sulfur precipitate is formed. So the rate of reaction is measured by calculating the time taken for the sulfur precipitate to form. But of course, the question is, how do I know when to stop my stopwatch, right? How do I calculate the time taken in this case? So if you see on the left side over here, this picture, right? You will notice that there will be flasks on the left and flasks on the right. The left one is before the reaction. The right one is after the reaction. I know your notes have no color, but this is how it looks like. Okay, it's supposed to be a cream color and a mushroom soup like that. So the left one is clear, colorless. The right one is like mushroom soup color. You know the Campbell's mushroom soup? No, it's not nice. I like the soup. Maybe it is. Of mushroom soup. You'll never see mushroom soup the same way again. All right, okay. Listen. So before you do the experiment, you have to prepare several things. Number one, you have to prepare the solution of sodium thiosulfate. You have to prepare the solution of hydrochloric acid. You can also replace hydrochloric acid with any other acid, such as sulfuric acid, nitric acid, and so on. Okay, so you can replace the acid of any types. Okay, now, before you start the experiment, you prepare the solution already. Then you have to use an A4 paper or any paper. You're going to use a marker pen to draw an X on the surface. Okay? And then after that, you're going to take the flask that contains the sodium thiosulfate. You're going to place it right above that X that you just draw on a piece of paper. And then get ready your stopwatch. And then you're going to pour in the hydrochloric acid. The moment you pour in the hydrochloric acid, you will start the stopwatch. And then you'll swirl the flask slightly to mix it around. And then place it back on the X and wait until the sulfur precipitate is formed. And when the X is no longer can be seen already, then you stop the stopwatch. You can repeat the experiment 3 times to get a more accurate value if you want to. Okay, but that's the basis of the experiment. You understand? So again, put the X on the paper, take the sodium thiosulfate solution, pour on top of the X, add the acid inside, press start on the stopwatch until the yellow precipitate covers the X. Then you stop the stopwatch, record the time taken for the X to disappear. All right, that's how we do the experiment. If you were to use different concentration of sodium thiosulfate while keeping the concentration of acid constant, you will realize that the time taken for the cross to disappear will be different. The more concentrated the substance is, the more concentrated the reactant is, the faster the cross will disappear. The faster the X will disappear. Because the sulfur will form faster. You understand? So if we have a higher concentration, while keeping the acid constant, of course, right? If the sodium thiosulfate's solution concentration changes, the more concentrated it is, the faster the sulfur precipitate is formed. Then the lesser time taken for the X to disappear. So that means that the higher the concentration, the higher the rate of reaction. Okay. So if you were to draw the graph, if you were to plot the graph of time taken for the X to disappear against the concentration of sodium thiosulfate, you realize that the concentration of sodium thiosulfate increases. The higher the concentration of the sodium thiosulfate, the lesser time taken for the X to disappear. And that means that your rate of reaction will increase. That's it. Do you see that? That's the correlation. Now, in exam also, sometimes they might ask you to plot something called concentration over rate. Okay. So besides the graph like this, time taken for cross to disappear against concentration, or that's not we saw another graph, that's not we saw, right? We plot what the volume of hydrogen gas over time. There is another graph that you must know, which is known as concentration against time, against rate. So imagine right now you have concentration against rate. The rate is equivalent to 1 over time. So if you were to plot concentration against 1 over time, you will get a directly proportional graph. Okay, you will get a directly proportional graph, which tells you that as concentration increases, the rate of reaction will also increase. Hmm? Okay. Now, why does increasing concentration will lead to an increase in rate of reaction, or in a decrease of time taken for the cross to disappear? I'm going to show you a video first, how this experiment is done, because on Tuesday's class, I showed the students how to do this experiment. So we will take a look at that. Okay, so you can watch this video and see roughly how this experiment is done. And then we'll continue on later on to discuss the factors.
This next demonstration I'm going to do is one that I've probably been doing for some 20 years. And the first time I saw it performed, I thought, boy, I hope I can do something like that. Because it was so interesting to see chemistry taught with a demonstration and the talking. And Dave Tanis was my inspiration. When I saw him do it, I decided I needed to go to more workshops. But this is a kinetics demonstration that I've since used mostly as a lab. It can be done on the overhead projector and all the students can gather data together, or you can have them do it back in the laboratory. It's a clock reaction, essentially. Let me go to the board for a minute and write the equation. We're going to take a sodium thiosulfate, and we've got a 0.15 molar solution of sodium thiosulfate. And we're going to add to that hydrochloric acid. All right, and I've only got the net ionic equation because the sodium and the chloride ions are spectators. This forms solid sulfur, sulfur dioxide and water. This solid sulfur is a colloid. It stays in suspension, and it'll eventually block the light coming through my beaker. You may have done this reaction as part of a chemical sunset, because there's a nice demonstration people do when they're putting it on the overhead projector, and they can see as the colloid forms more and more. But we're going to do it as a lab, and we're going to be talking about concentration. And what I've done is I have 5 beakers, and the beakers have varying concentrations of the thiosulfate. So in the first beaker, of course, I've just got the pure 0.15 molar sodium thiosulfate, and then I have diluted it along the way. And I would give my students a data table like this and ask them to calculate those new concentrations for the other 4 beakers. We're going to add 5 milliliters of hydrochloric acid, and the students are going to observe the disappearance of an X as that colloidal sulfur forms. So we need to time this, and can I get a volunteer? Janet, I'm going to tell you when to start and when to stop. And I'm going to put the sulfuric acid in here and then, hydrochloric acid, and then, tell you to start and then stop. Start. All right, now I'm going to tell you when that X disappears. If you look from the side, you should start to see the cloudiness on the side. All right, now you're looking down. Stop. Okay. How many seconds did that take?
18.68.
18.68 seconds. All right, and what the students, thank you. I'm not going to do the whole experiment for you, but what the students would do usually, if I have them do it as a lab, they'll do each part. And I always warn them. I say to them, start the last one early, because it's going to take longer for that last one to change. And what we do is we start measuring. We put the other ones in. And they will take varying amounts of time to change, and the kids time them. The last one frequently takes like 3 to 5 minutes to change, and so if they don't start that one early, they'll have some problems, but they will get a sense of the rate, and we do the first one early so that the kids get an idea of how to mark that X. And they'll just change it. So it's concentration versus the rate. And let me show you what the data would look like for something that I did do in my classroom. We'll do a cooking show approach to this. This is some actual data that my students gathered. And you see that in this case, their initial one was 22 seconds, and their final one was almost 3 minutes. Right. We're going to look at the graph, if we plot the concentration versus time. So if I plot concentration versus time, it's not linear. So I talked to the kids about the fact, well, what about rate? If you're looking at rate, the more time it takes, the slower you're going. So it's really an inverse relationship. Let's look at the graph of concentration versus 1 over time. So it's easy for kids to do this now with those graphing calculators, and so I show them how to make lists and use their graphing calculator, and they will get a linear relationship for this. You can talk about the fact that this is the concentration in this case is directly proportional to time. If you're teaching a class where you talk about rate constants, you can say this is first order with respect to concentration. Otherwise, you can just talk about the fact that it's an inverse relationship, but it's directly proportional. And you can ask them, well, how could I test to see what the relationship is with the amount of acid? There's 2 reagents involved, the thiosulfate and the acid. We kept the acid constant. Let's see, could you tell me how to alter the experiment? And that would get them thinking about variables that they'd have to hold everything constant, and except for the HCl concentration, and they could make a similar graph of that. It's a great experiment. It has a lot of extensions. They could even look at the effect of temperature on rate with this experiment. And
So generally, that's how the experiment is being done, right? Where you can see that the rate of reaction is directly proportional to the concentration of sodium thiosulfate. And what the lady said just now is that you can also change not just the concentration of sodium thiosulfate, you can also actually change the concentration of the acid used. So instead of changing concentration of sodium thiosulfate, you can keep the concentration of sodium thiosulfate constant, but at the same time, you can change the concentration of acid. You'll get a similar result. So the question is why, right? Why does the, let me just share my screen. Why does the concentration actually affect the rate of reaction? So this is the mechanism, okay? This is the mechanism wise. So if you have this, right, you see here, why does increasing concentration actually increases the rate of reaction? Again, we are going to explain this in terms of collision theory, okay? So by increasing concentration of the reactants, you should have more reactant particles. Make sense? If we increase the concentration of particles, you should have more reactant particles. Make sense? So when you have more reactant particles, then there will be technically more collisions. That's not. If you have more reactant particles inside the same container, you should have even more collisions. So you see over here, more particles can collide among one another. Makes sense, right? Imagine initially you have only 100 particles inside. And then you increase the concentration, you get 200 particles, 300 particles, 400 particles, 1,000 particles. So you have more particles there to collide with each other, increasing the number of collisions. And once you have more collisions, obviously, you will have a higher chance of getting even more successful or effective collisions. And when that happens, automatically, the rate of the formation of your product will start to increase. So based on that, 3 points again, you see, increasing concentration means more reactant particles, which will lead to more collisions and eventually leading to more successful or effective collisions. That's how we increase the rate of reaction. So in exam, if they ask you questions associated to concentration of substances, all right, that affects the rate of reaction, this is how we should explain it. Usually 2 to 3 marks, you have to write all the points inside here in respect to collision theory. Okay, clear? So how many factors are there? Surface area and concentration. The next one is called pressure, the third factor that's going to influence your rate of reaction. For pressure, it only affects gases. Okay, for pressure, it only affects gases, nothing else. Not liquids, not solids, gases. Okay, now, very easy to understand. When pressure increases, volume decreases. When pressure drops, volume increases. We said that pressure is inversely proportional to volume, correct? Make sense? So imagine right now, I have gaseous particles inside a system that's going to react with one another, okay? And I increase the pressure inside. When you increase the pressure, volume starts to drop. That will push the particles closer to each other. Make sense? Just like, for example, I ask all of you to blindfold yourself and walk in the classroom randomly. Imagine this classroom got no table and chairs. You just walk randomly. You ask yourself this question: how often will you collide with your friend? If the larger the space, the less likely you collide with each other, correct? Now imagine right now I cut the size of the classroom to half. And I ask you to walk randomly, same number of people. There'll be a higher chance of collision. And if I divide the room to 4 and place you in one corner, a quarter of the room, even more collisions. So the same concept applies here. When you have higher pressure, you're pushing the particles closer to each other. So the closer they are, the easier it is for them to collide with each other. So the particles will start to collide even more often, causing an increase in the number of collision as well as number of successful collision. And that will also increase the rate of reaction. Since this one is related to concentration, that's why I put it together with concentration. So don't have to stress out too much in learning all these things. The only thing you need to remember here is that pressure only affects gases, because only gases can be compressed. Understand? So how many factors are there already? Surface area, concentration, pressure. Right? Very easy, right? Okay. The next one is the fourth factor, which is temperature. Okay? For temperature, we're going to use back the same reaction. Right? We see that there's not increasing concentration of sodium thiosulfate increases the rate of reaction. But what if I keep my concentration of sodium thiosulfate and the acid constant? But what I do is I change the temperature of the sodium thiosulfate in different set of experiment. That can actually also affect the outcome of the rate of reaction. All right. So when the experiment is carried out in different temperature, for example, I use different temperature of sodium thiosulfate. Maybe I use 25 degrees Celsius and I increase it to 35 degrees Celsius, then 45 degrees Celsius, 55 and so on. For example, I keep on increasing temperature and see what happens in each time. You realize that the more I increase the temperature, the higher the rate of reaction. So which means over here, when my temperature increases, the time taken for the X to disappear also decrease, which means the sulfur precipitate will form faster. You understand? So again, if you were to draw the graph of temperature against 1 over time, which is technically temperature against rate. You will get a directly proportional graph. That tells you that temperature is directly proportional to rate. Okay, do you understand? So you can see it's getting easier and easier because in your mind, you are already set in the collision theory. That's what I want. I want you to always remember the collision theory. But for this example for temperature, it's slightly different. Besides collision theory, the kinetic theory of matter is also involved. Let me show you. So the question now is, why does increasing temperature will increase the rate of reaction? So this time, we're going to use two different concepts to explain the same situation over here. Number one is when temperature increases, the reactant particles will start to gain kinetic energy. That's why it's now related to kinetic theory of matter. Do you see that? As temperature increases, the reactant particles will start to gain more kinetic energy. And when that happens, they will start to move even faster. Imagine right now I ask you all to blindfold yourself and walk around the class randomly. All right? You will find it quite hard to collide with each other, correct? If you blindfold yourself and ask you to walk randomly. So you have a lesser chance of colliding against your friend. But what if you run? Instead of walking, what if you run? Isn't it easier to collide with another friend? Concussion, correct. So my point here is the same thing. When you increase the particles' kinetic energy, they move faster. Therefore, there will be a higher rate of collisions. When there is more collision between the particles, wouldn't they form more products? Wouldn't there be a higher chance of getting successful collisions? Yes. So as the higher speed, when they have a higher speed, then there will be more collisions between the reactant particles. When that happens, that will create even more successful collision and therefore increasing the rate of reaction. But you must understand that the particles are gaining that kinetic energy. That's why they are moving faster. So which means in exam, you are also required in this case to also explain the situation in terms of kinetic theory of matter. You understand? Only for temperature. So sometimes they will ask you the other way around also. What if I reduce the temperature? What happens then? Yeah, decrease the rate of reaction, right? Why? Because the particles will lose kinetic energy. They will start to move slower. Lesser amount of collision, lesser chance of successful collision. Then the rate of reaction shall drop in that sense. You understand? So, if you notice, so far, 4 different factors that we talk about, they are all in this way, right? When they explain all these mechanisms, they have almost the same answer. The goal is very simple. The goal is to get higher number of collisions. The goal is to increase the number of successful collisions so that you can get more products. That's it. Okay, so the first 4 factors is all about getting more collision and more successful collision. The only difference among the 4 factors is the initial line that you use. How can it lead to that higher number of higher number of collisions? How does it lead to that? That's the only difference between the 4 factors that we talked about earlier. You understand? Okay. Now I'm gonna skip light and come back later. Okay, I'm gonna skip light and I come back later. We'll go straight to catalyst. Catalyst is a chemical substance that can alter the rate of reaction by providing an alternative pathway for the reaction to occur with a lower amount of activation energy. What is activation energy? The minimum amount of energy required for the reaction, correct. If you go back to the front page, you remember me telling you about this. Sufficient amount of energy. This sufficient amount of energy is your activation energy. Which is also known as EA. So what's activation energy? Minimum amount of energy required to kickstart the reaction, correct? So what happens if you don't achieve this minimum amount of energy? What if we don't achieve this minimum amount of energy? Then what happens? They don't form products, correct. There could be a collision, there could be collisions, but without amount of energy, you cannot form products. That's why initially in the collision theory I explained to you, colliding the particles together is not enough. The collision by itself is not enough to form products. The collision must fulfill the requirements. For example, achieving the activation energy and also colliding in the right orientation. So this is where catalyst comes into play. Over 90% of all industrial processes require a catalyst because most of those chemical reactions are too slow to sustain the business, right? If you're a businessman, how do you reap profits? How can you get more profits and get rich? Sell more. Do you realize that businessmen always tell you the same thing? They will say that time is money. Why is time money? Because if you can produce more products in a shorter period of time, you can sell more. For example, right? Let's just take for example, okay? Guy A sells durian. Guy B also sells durian. But guy A only sells 10 durian per day. Guy B sells 100 durians per day. Why? Because he's better, is it? Because he's more length, is it? No. Whoa, so old man. Price. No, because he has 100 durian, this guy got 10 new. You get it, you know? So the thing is all about production. We want it fast so that we can sell more. When you sell more, you get more profits. In the industry, manufacturing of substances must go fast. Everything must be fast. If it's too slow, you don't get the profits. You're wasting time, you're wasting energy, you're wasting resources. So that's why most of these industrial processes involving chemical reactions, they all require catalysts to speed up the chemical reaction. Okay, so what is a catalyst? A catalyst is a substance which can alter, so just change this word for alter the rate of reaction. The question is how? It helps by lowering the activation energy required for a chemical reaction. You understand? Okay, so a catalyst can alter the rate of certain reactions without being chemically changed itself. I'll explain to you more about this later on, okay? Without being chemically changed itself. It goes in, it helps the reaction, it comes out. That's it. It's like, for example, this guy wants to cheat on this girl. Yeah. Example. Okay, this guy wants to chase after this girl. And then this guy has a wingman. Does the wingman go and chase the girl? Does the wingman chase the girl? If yes, then that's not a wingman. That's a traitor. This is an example. My point here is the wingman goes in, help the guy and the girl to be together, and he comes out. He's not involved in the relationship. Not in a weird way, okay? No. This is the point. So the catalyst is like the wingman that helps the relationship, but doesn't get involved in the relationship. You understand what I mean?
It's like, crazy in a virtual.
No, I'm just saying it's an example. So the catalyst goes in, helps the chemical reaction, comes back out. It does not get used up. It is not chemically involved. So after the reaction, if you add 5 grams of this catalyst into the reaction, at the end of the experiment, you still get 5 grams of the catalyst. It doesn't get used up. You understand? That's why it sits here chemically unchanged. Now, the effect of the catalyst can be seen in one simple example. Decomposition of hydrogen peroxide. What is hydrogen peroxide used for? What is hydrogen peroxide used for? H2O2 is hydrogen peroxide. Yeah, but what is it used for? Can we drink hydrogen peroxide? Because you can drink H2O, right? Why can't I drink H2O2? It's just an extra oxygen inside. Huh? If you drink hydrogen peroxide, you'll die. Right? Because H2O2 is unstable, it will break down to release O2 and H2O. But the process is really slow. Okay? H2O2 is used as an antiseptic.
A what?
Antiseptic. You know iodine?
Yeah.
When you fall down, you hurt yourself, they put the brown color liquid, what's that? Iodine. But some people are allergic to iodine, what do they use? H2O2. Diluted hydrogen peroxide. Now, why is it effective? Hydrogen peroxide produces something called reactive oxygen species, which can kill germs. All right? That's why I say if you drink H2O2, you'll die. Okay? The process of decomposition of H2O2 is really slow. It's really slow. All right? So how do we speed up the chemical reaction? By adding a catalyst called manganese oxide. Yes, it is a part of special elements. Manganese oxide is MnO2. You add a little bit of manganese oxide inside, it will accelerate the decomposition of hydrogen peroxide. Okay, so the moment you add manganese oxide inside, you will start to see bubbles coming up. Bubbles of what? Bubbles of oxygen forming. So that tells you that when you were to add this manganese oxide inside, it will accelerate the decomposition of hydrogen peroxide. Does the manganese oxide get used up? No. If you put in 5 grams, how much will you get back? 5 grams. Because the catalyst does not get used up, does not change chemically by itself. It can be reused over and over again. And the best part about this catalyst is that you only need a very small amount to have a very big change in the chemical reaction. No. The only disadvantage of this catalyst is that two disadvantages. Number one is that it must be pure. Number two is very specific to only certain types of chemical reaction. You cannot use the same catalyst for every single chemical reaction. That's the catch. So for a specific chemical reaction, you have to look for a specific catalyst. That's how it works. Okay, I'll stop here for today. So I explain to you more next week. Today is the 20th of October. Questions? If you have any before we leave? No. By the weekend? Okay, nothing else. I'll see you guys next week. Thank you.